Assalamualaikum and hi everyone, and this is still in chapter 7 mechanical properties of the metals and alloys, but in the part 2. So the outline for the part 2 is 7.3 elastic and plastic deformation, 7.4 stress and strain diagram. The learning outcomes, you're going to state the Hooke's law, the Poisson ratio, and note the conditions under which it is valid to describe the differences between the elastic deformation and plastic deformation, to determine the modulus of elasticity, the tensile strength, and to estimate the percent of elongation and ductility in terms of the both percentage elongations and percentage of the reductions of area for a material that is loaded in tension to fracture from the stress-strain diagram. So give brief definitions of the modulus resilience and also the toughness in the mode static. So we begin with the elastic and the plastic deformation. We know that the metal undergo deformation under the uniaxial tensile force. Okay, so what is actually the elastic deformation? So the elastic deformation in which the stress and also the strain proportional, which is we call it as the elastic deformation. Alright, so metal elastic deformation is a non-permanent, which means the metals return to original dimensions after the tensile force is removed. What we call as a reversible, the deformation are instantaneously recoverable. So you can see from the figure over here how actually the location of the atoms still in the chain, even though it's still in the force where it been pulled in the x direction. So for the plastic deformations, the metal is deformed to such an extent such it cannot return to its original dimension. So what we call as a irreversible or non-recoverable, yeah, by the time that it's elongated or at the time that it's been fractured. Okay, so this is actually the common stress strain curve. Yeah, we can actually obtain this diagram, yeah, for specific materials by performing a tensile test. Yeah, for example, so this involves by applying a known force, yeah, to a test piece and measuring the stress and strain in the test piece as the applied force is increased. So if you can see over here where it's actually the proportional limit, the elastic limit, or we call it as a yield point, yeah, the fracture point, the plastic behavior, the elastic behavior, and also the permanent set. So this is actually covered, yeah, important parameters, which is the stress, the strain, the elastic modulus, as well as the Poisson ratio. And this is all depends on the loading mode. It can be in the tension, or it can be in the shear, or maybe can be in the compression. Okay, the details how actually the stress strain behavior, yeah, because each of the points actually represent different of the behavior of the materials. So then that one will be covered in the section 7.4. Right, so the stress strain behavior in terms of elastic deformations here, you can see it can be divided into the two sections. Okay, so the schematic stress strain diagram here showing the linear of the deformation for the loading and unloading cycle. Okay, so you can see over here, yeah, by the time that the movement of the sample can be shown from the normal stress and also the nominal strain. Okay, so deformation that is a non-permanent, the deformation that occurs in which stress and strain are proportional. So this is the result of the plot graph. Stress and strain is a linear relationship. Yeah. Also that we can actually, from this diagram, we can actually find find the other of the properties, yeah, which is the models of resilience, yeah, which is the under the shaded area, under the elastic deformation, Okay, also that we can show how actually the modulus resilience is being defined from the diagram. So what is actually the resilience? Resilience is actually the capacity of the a material, yeah, that can be absorbed energy to reverse back, to recover. So this actually associated with the property in the modulus of the resilience, which is denoted by the U R. Yeah, R is for the resilience. Okay, so you can see here the elastic definition also show you the reversible. When the stress is removed, the material returns to the dimension it had before the loading. Yeah, and usually the strain are very small. Yeah, except for the case of the plastic. Okay, so if you can see here, the strain is very small compared to the region of the plastic is much longer, and the plastic deformation is irreversible. When the stress is removed, the material does not return to its previous dimension. So as shown in this animated stress and strain. Okay. So from here, you can identify the Young modulus, even the Poisson ratio, and we can know where is actually the proportional limit and also the elastic limit. Okay, so it is also represented over here how actually we can see at the atomic diagram over here, where at the initial the atom actually stretch apart, yeah, but no bonds actually broken. So the test piece begin to stretch, but the strain is still small. Yeah, you can see this is a strain, it's still small. And after the load is released, the bond actually return to the original, yeah, which is the unstretched positions. So in this case, what we call as the elastic deformation, we can return back to the original place. So this is actually the diagram or the animated to show you by the time that it been pulled and it's still coming back to the original shape of the diameter. In terms of the atomic scale, which is the microscopic elastic strain, is defined as the small changes in the interatomic spacing and the stretching of the interatomic bonds. Yeah? So as a consequence, the magnitude of the modulus of the elasticity is a measure of the resistance to the separation of the adjacent atoms. That is the interatomic bonding forces. So it also show you that the slope of the stress and strain plot, which is proportional to the elastic modulus, it depends on the bond of the strength of metal. Yeah, so this is show you the strong of the bonded, and the bottom show you the weakly of the bonded. So this picture show you the force versus the interatomic separation for weakly and strongly bonded atoms. Okay, so for the Hooke's law, basically is what we call as a modulus elasticity. Okay, the Hooke's law usually only applies for the small strain. Yeah, for larger strain, the relationship between the stress, yeah, with the strain is no longer linear. So here, the degree to which the structure deforms of the strain depends on the magnitude of any imposed stresses. Yeah, for most metal, there are stress in the tension, and stress and the strain are proportional to each other through the relationship. But remember that it is if the what they call the strain is larger, it is not reliable anymore. Okay, so this is here, which is the E is actually your modulus of elasticity, or namely as a Young modulus, yeah, and the unit is a Pascal or can be in the Newton per meter square, and it's noted by the stress. And the E is actually the slope. You can also get the value from the slope of the graph. Yeah, so in this case, it shows that the linear elastic where still that the stress is proportional to the strain. Yeah, where the strain is still smaller. But the time that when come to the exceeding of the plastic, here we cannot use anymore the terms of the stress proportional to the strain. So as the stiffness of the material resistance to the elastic deformations, the greater the modulus, the stiffer the material, or the smaller the elastic strain that result from the application of the given stresses, the loads, and also it's important that designer parameter used for computing the elastic deflection, especially when we want to design, example, we want to design the beam or the bridge, where we can actually withstand the bending or the deflection due to the external forces imposed onto the beam. Right, so this is actually a figure which is, shows the range of the elastic modulus here. You can see it shows you the modulus in terms of the metals, the ceramics, polymers, and also the composites, which is for the various of the engineering materials. So in this case, the E for the plastic or for the polymers, which is we can see from here, is much smaller or lower than that for the other of the material, which is the metal and also the ceramic. However, we can see the what they call the modulus, the Young modulus for the composite over here, especially for GFRC or maybe for the carbon, lies between the values for the matrix between the polymer as well as for the fiber phases. It depends on the how much actually the fiber content of the fiber or the reinforcement content. The more the fiber or the reinforcement content, the better the Young modulus, because it gives you the high stiffness. For the modulus for the ceramic, it's quite high. You can see it's quite high. Generally up to the 400 or more than 410 gigapascal. So this is because of the strength of the ionic and also the covalent bonds makes the modulus is higher compared to the other of the group materials. Okay. So this is a next property. This is very interesting. The Poisson ratio, which is such important material property because it can give understanding how actually the different materials can be deformed under the different loading. Okay, so you can imagine that, when the tensile stress imposed on the tensile stress is imposed on the metal specimen, an elastic elongation and accompanying the strain result in the direction of the applied stresses. Okay, so we basically can correlate it with this picture. Okay, as a result, in these elongations, there will be the constrictions in the lateral, which is at the x-axis and also y-axis directions, perpendicular to the applied stress. Okay, so here, imagine that in this picture, they're giving you in the compression or the extraction. Here, by the time that it's actually been pulled, the sample is actually starting to the elongator. However, if you imagine that if in the compression, the other way, so we can imagine that is a cube, same in the cube, and you will give the what they call we compress it, it will expand. The size will be expanded. However, the direction of the force, it give you the height of the cube become more shorter compared to the width will be expanded. So this is a direction in which the perpendicular to in which we apply the loads. So this is actually the way that actually, for example, this is a force be applied perpendicular to the direction of the expanded. Okay, alright. So the load direction, what we call as the longitudinal. This is the longitudinal, and the what we call the perpendicular. This one is actually the lateral axis. Okay, so this is actually longitudinal. Right. So what we can say that the ratio of the lateral and also the axial strain is called as a Poisson ratio, denoted by the V. Okay, so normally the theoretical, most material have the VR between the 0.0 up to 0.5. So a perfectly incompressible isotropic. So this is actually the theoretical value for isotropic material, which is 0.25. The isotropic material means that the material have the same properties at all directions. Okay, so anyway, the PR can tell us how much actually this material will contract in lateral positions, in which we pull it at the longitudinal direction. Okay, they give some information how much actually it can be changed at the lateral, and at the longitudinal. Okay, so in this case, this is actually the formula that we given. Alright, so whereby that we know that, for example, that the strain at the x-axis, yeah, is equal to the changes length at the x-axis divided by the length at the x-axis, or we can say that at the what they call the strain at the y-axis, here equivalent with the negative x here, Lx divided by the line at the y-axis. Yeah, so the negative is actually showing it is in the contraction. Yeah, meaning it's in the compression. The signs will be negative, right? And another one is we basically also use the epsilon or x strain. The strain at the z direction is equal to the changes of the length at the z equal to the divided by the length original at z. So basically the EY, the strain over the EX is equivalent with the strain at the Z direction, yeah, over the EX. Yeah, so this is actually equal to the material constant. Right? So this is the material constant where we denoted as the nu, this one. Yeah? Noted as a nu. They call it as a nu, which is equivalent with the strain at the lateral divided by the strain at the elongation, okay, or longitudinal. Okay, so the sign of the negative over here is actually slipped into the equation to ensure that all the values that have been calculated is always in the positive, right? Because we cannot avoid that by the time that if you impose the compression, of course the value will be negative. Yeah. So in order to avoid the sign of negative, then we put the value, we put the sign, we slip the sign of the negative onto the formula, ensure that all the value that we obtain is always in the positive, right? So this is actually the relationship here between the elastic modulus, which is denoted by E, and the shear modulus denoted by G. Sometimes in some books, they call it as the rigidity modulus denoted by G as well. So for isotropic materials, the shear and elastic moduli are related to each other. So where is isotropy is having identical values of a property in all crystallographic direction. Okay, during before the unloaded and after the unloaded. So we can see that the phase is actually being shifted, yeah, at the degree, at the specific degree. So this relationship, yeah, the shear stress to the shear strain can be concluded into this formula, where the tau, the shear stress, the equivalent with the modulus rigidity or the shear modulus toward to the shear strain. Okay, so for the isotropic material, it can be used the E modulus equal to the 2 modulus rigidity with the mu, okay, which is normally it's a 0.4 of the modulus elastic. Okay. So this is the other of the elastic properties which is related. Yeah, which is we can see here the elastic shear modulus G, here represented under this formula, the tau equal to the modulus rigidity with the shear strength. Yeah, and also the elastic bulk modulus, which is denoted by K, where K is actually the constant, P equal to negative K with the changes of the in volume divided by the changes of the original volume, right? And the special relationship for the isotropic material can be concluded into these two formula. Alright, now we consider this example. It can also be used here. This example is similar like the previous. It does that on here. We want to show the connection, the usage of the what they call the formula here between the modulus and also the strain. So if you can see here, this deformation situation is represented in the accompanying drawing. Here, by the time that you will be given the question, you can actually uh, 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 take out all the information and do some sketches just to show that how actually the information can be translated into the diagram. So in this case, it shows that the positive ratio at the z-axis equivalent with the changes in the line divided of the line original. Yeah, which we can see that this is I represented instantaneously continuously of the changes. Yeah, minus the original divided by the original. So how about the x? And the x-axis, the strain is about the diameter. Okay, so you can see here, the direction which is represented over here. So the strain at the x-axis, which is whether it is expanded or contracted. Okay, so the di minus d naught over the d naught. So when the force F is applied, by the time that you pull the member, you can imagine that this shape is actually being elongated at the same time the size being reduced. Yeah, so the specimen will be elongated in the z directions and at the same time experience a reduction in diameter, which is denoted by the changes in diameter of 2.5 times 10 power of negative 3 millimeter in the x direction. So for the strain in the x direction, we can actually calculate the changes of the diameter. So the epsilon over here, the epsilon x, the strain at the x-axis is equal to the changes of diameter over the original diameter, which is you will obtain the value in the negative, which negative since the diameter is reduced. Yeah, so don't get wrong. This is not a new, not the positive ratio, which is always in the positive, but this is actually the strain. The negative is actually indicate as the diameter is reduced. Right? So if there's no negative, it is actually indicates as the diameter is increasing. Right, then we move to the step 3 where in the next become necessary to calculate the strain in the z direction using the equation 6.8 here, which is similar the formula, but in this case because they give you the Poisson ratio through the table, you can use the Poisson ratio to compensate it, and thus the what they call the strain at the x-axis is equal with the negative of the strain at the x-axis divided by the nu. Then you substitute all the values, you will obtain 7.35 10 power of negative 4 without any units. Remember that for the strain, it is a unitless or dimensionless. So the applied stress may now be computed using the equation 6.5, which is under the Hooke's law, and the modulus of the elasticity given in the table as a 97 gigapascal. Okay, as the stress, we can say the modulus equal to the stress over strain here, but then you rearrange back the formula as you want to know the value of the stress. You put the stress on the other side and the rest with the values the other sides. So substitute all the values, then you will obtain the answers for the 71.3 megapascal. So then we will substitute the value under the formula stress equal to the F over A. In this case, they are looking for the force. We rearrange the formula into the F equal to the stress times with the area. Okay, then substitute the value, you will obtain the what they call the force is 5,600 Newton or 5.6 kilo Newton. Okay. Alright, so by definitions, now we move to the plastic deformation. Okay, in this plastic deformation, if you can see here, the figure they show you there's a two figure over here. Okay, definition is not reversible when the stress is actually uh, stress is removed and the material does not return to its previous dimensions. Okay, so deformation occur which is the stress and strain are not proportional. Yeah, so for most metallic elastic deformation, persists only to strain of about 0.05 at the strain diagram, yeah, you can say that it is actually exceeding the elastic. Yeah, so as material is deformed beyond the point of 0.005 here, yeah, it say that the stress is no longer proportional to the strain, whereby that we can say that Hooke's law is not being applicable anymore. So then we call it as a permanent non-recoverable. So here, if you can see from this picture, this schematic of the what you call the tensile test, stress strain, yeah? The stress and the strain behavior into the plastic region is typically drawn as such like this. This is A we represent and this is B we represent. So the transition basically, transition from the elastic to the plastic here, yeah, is a gradually. Yes, some curvature result at the onset of the plastic deformation. For example, we can say over here, yeah, for example here, yeah, the plastic deformation, which increase more rapidly with the rising of the stresses. Okay, so this is where that you have an upper yield point and lower yield point. So this is actually represent where the onset of the strain hardening, yeah, where it's actually the point of the strain hardening will start. Okay, so if you can see from here, it actually is almost similar, whereby the stress and also the strain, the sample starting to necking after exceeding the elastic region. Okay, and by the time it reach at the maximum of the stresses applied to the sample, the necking is starting to reveal before it comes to the fracture. Okay. So this is actually that you can see how it can be represented. Yeah, it can be represented by this diagram. So this is a plastic deformation, and another one is a resilient, which is already explained it to you. It's about the ability to restore the energy. Okay, alright. So this is also the how actually the arrangement of the atom by the time that you give some force, yeah, exceeding to the elastic limits, yeah. So we can see that it become at the slip, yeah, where it changed actually the bonds, yeah, the bond have been break. Yes, so this is actually why we can see that how actually it's been show the plans. Yeah. So first initially it give you the kind of what they call the breaking bonds is still not present. By the time that it entering the second, yeah, which is exceeding the elastic limit, we can see actually the bond is stretching and the plans start to shearing. Right, which is here in terms of the changes, yeah, of the strain. It shows that it's a combination between the elastic and also the plastic. But by the time that is starting to entering the plastic, it shows that by the time you unload, the plane still is sheared. It cannot be returned back to the original. And so this is what we call as the changes is in the plastic region. So by the which is show you from the final element analysis over here how actually the necking already took over of the sample strength. So from atomic perspective, plastic deformation corresponds to the breaking bonds with the original atoms neighbor and reforming the bonds with the new neighbors. As a large number of atoms or molecules move relatively to another, upon removal of the stress, they do not return back to their original. Yeah, as you can see from here. Alright. Okay, now we move to the last part of this section. It's a stress strain diagram. Okay, so what is actually the material strength? Yeah, what is actually the material strength? It's a measure of the stress a material that can withstand. Yeah, so in this case here, you can see that there's a couple of the mechanical properties here that can be obtained from the engineering tensile stress, especially after you are plotting the stress strain diagram. So mostly the most common mechanical properties is a modulus elasticity, the proportional limits we denoted by P, and the yield strength at the offset of the 0.2% offset, and the tensile strength, yeah, what we call also as the ultimate tensile strength denoted by the TS, and the tensile strength at the fracture with the unit of the megapascal, and lastly is the ductility. Okay, so we look first with the yield strength at the 0.2% offset here, which is denoted by the sigma at the yield point, and the unit is in the megapascal. Okay, so the yield point is basically a material here of the material occurs when the material transition from the elastic behavior here, where it's actually removing the applied load, we return back to the original here, to the plastic behavior where the deformation is permanently. Okay, so in this case, the yield points here, definition by definition, denoted by the P. Here, you can see over here the P. Here is the first point where the load at which the specimen yields, where the specimen cross-sectional area begins to decrease. Here, it neck down. Here, significantly, or an increase in the strain occurs without an increase in the stress, and the strain deviates from being proportional to the stress. Okay, so how you find, yeah, you find this value, yeah, by making the divider method. Okay, so how you make the divider method in this case, because you will apply the offset. So we can see the typical stress strain behavior for the method showing the elastic deformation, the proportional P, as well as the yield strength, which is you need to determine using the offset strain 0.02 strain offset. Okay, so in this case, you are what I call you are using the value 0.02 starting from the origin towards to the strain 0.02. You will make a straight line until you reach to the where that the line is actually cross, ataupun intersect the ideal of the curve over here. So that is actually what we call as your yield strength. Okay, so in here you have two types. Yeah, sometimes in certain materials you can identify there's a upper, yeah, upper yield strength, yeah, yield strength, and also have a lower yield strength. Not all material has it, but some material will show you a two different of the what they call a value of the upper and lower yield strength. So the upper yield strength is actually the strain hardening, and the lower strength is actually where the strain hardening is starting. Yeah, is starting to happen. Okay, all right. So how about the modulus of elasticity? EGPA over here is in the gigapascal. G stands for giga, which is the value is 10 power of 9. Yeah, 10 power of 9. Okay, so it's also known. Yeah, it's also known. What they call also known as a modulus. Remember that before you do the modulus elasticity, the offset yield strength you need to do first. Yeah, where the offset yield strength just now is an arbitrary approximation of the material. Then the elastic limit is the stress where it is corresponding, yeah, to the point where they intersect and the stress strain curve, and the line which is parallel to the specified modulus, yeah, which is in the modulus elasticity, in which is follow the Hooke's law. Okay, so once you already calculated or identify your yield strength, then you can calculate your modulus elasticity. Okay, in this case, there's the modulus here. If you can see, here the stress and strain are linearly related in the elastic region only. For example, in this case, here, this is an elastic, this is actually the plastic. Here, higher the bonding strength between the atoms, so the higher is the modulus elasticity. Yeah, the stronger actually the atom been hold together, yeah, the harder actually the bonds to be breaks. Okay, so for example, actually here the modulus of elasticity of the steel is a 207 gigapascal. Yeah, and the modulus of elasticity of the aluminium is 76 gigapascal. So what we can actually can summary from here, it shows that it is a 3 times the modulus of elasticity aluminium is 3 times compared to the steel. So this means that for the fixed geometry, for example, this is a geometry sample that you are tested. Example. Okay, for this kind of the fixed geometry, a part made out of the steel, yeah, made of the steel alumina or alloy 76, is a what do you call it, steel over here. Steel is actually is a 3 times, yeah, as stiff as it if it were made out of the aluminum, yeah. So it's a 3 times, yeah. Yeah, it is made from the aluminum. So for steel, yeah, has higher means that the steel has higher resistance, resistance to change, what we call to change in the shape, yeah, because it has a high modulus, very stiff, yeah, compared to the aluminum or the brass, we can say. So it is an inbuilt property of metal due to the arrangement of the atom itself. Okay, so that's why we can say from this value that you obtain for calculation of the stress given by the strain, yeah, or the changes of the stress and the changes of the strain means that this is your linear curve, yeah. This is your, for example, this is your strain 1, this is your strain 2, this is your modulus, your stress 1, this is your stress 2. So this is actually represent the stress 2 minus the stress 1 divided by the strain 2 minus strain 1. Yeah, the changes of the stress and also the changes of the strain in order for you to calculate the modulus of the elasticity. Okay. So for this third of the properties, how do you find? And how do you find this value? You need to refer to the maximum engineering stress, which is in tension, that may be sustained without the fracture. So in this case, here, if you can see here, this is actually the ultimate tensile strength. Here, by the time the maximum stress can hold, here can withstand. So what we call it as the ultimate tensile strength. Here, sometimes it can be called as a UTS. Okay, so remember that the stress strain diagram for the ductile materials, yeah, for example, like this, yeah, are shown that there is a initially region for the low strain over here, yeah, where the relationship between the stress and also the strain is linear. Yeah, deformation occurring in this region are fully reversed when the load is removed and so said to the be elastic. So this relationship, yeah, by the time that here you can actually correlate with the stress and also the strain. Okay, so this is actually the common, yeah, for the ductile material curve. Yeah, if you can see here, it show you if before the break, it show you the necking over here. Alright, so what does it mean about the necking over here? Here it means that before the necking, it is a here, this is a place where we call as a, show here total strain over here, it show that as a strain hardening. Yeah, so as I mentioned for just now, we have upper and lower of the yield strength, right? So it is actually the beginning of the strain hardening. Yeah, so it is where that you have the ultimate stress, and also that while the specimen is elongating, that time you can see this picture. Yeah, by the time that the sample is elongating, yeah, memanjang, yeah, it's a sectional, the x sectional area over here, yeah, will start to decrease. Okay, so this decrease area is fairly uniform over the entire gauge length. Okay, over the entire gauge length. So what will happen by the time they reaching the necking? what will happen after they reaching the necking. Okay, so you can see here the fracture strength, also known as the breaking strength, is the stress at which a specimen fails via the fracture over here. So at this, before the fracture, the necking is actually at ultimate stress. The X section area begins to decrease more and in localized region. Yeah, it been static into the one location only. As a result, the constrictions on necks tends to develop over here, where that the elongation of the sample will be furthermore. Okay, so this specimen finally will break at the fracture stress. So sometimes we call it as a stress fracture, denoted by the sigma F. Okay, sigma F over here. Okay, so this is a comparison. Yeah, the comparison of the sample in terms of the tensile strength, where we can see that in terms of the metal alloy and the composite is almost same part, even though it's slightly higher for the metals, yeah, compared to the composite. Yeah, remember for composite it depends on the percentage content of the reinforcement. So the more the reinforcement that you put into the composite, the higher of the strength. Yeah. Okay, and then the polymer here remain the same, the lowest one. Here remain the same, the lowest one. Alright, so here the example for the stress strain diagram, it can be represented, for example, for this. So we can see the mechanical property determination from the stress strain plots. So from the tensile stress strain behavior for the breast specimen shown in the figure 6.112, 6.12, determine the following. You need to find the modulus. As we know, the formula E equal to the stress divided by the strain, and the yield strength at the strain offset. Yeah, the strain offset, which is you need to get the value at the second diagram over here. The maximum load that can be sustained by the cylindrical specimen having an original diameter of 12.8 mm, yeah, and the change in the length of the specimen original 2.5 mm long that subjected to the tensile strength of the 345 megapascal. Okay, so what we need to do in the first step, because they are asking you the modulus, and we will take the value from the stress at the beginning and the stress at the final at the linear section only, at the linear section. This is actually have been zoomed out, to get a clear diagram. Okay, so over here we can see here the stress at the first part is actually 150. Yeah, not the first part, the second part is approximately 150. Yeah, minus the stress at the initial, which is 0, divided by the strain and divided by the strain represented by the stress location 1 is equal to the 93.8 gigapascal, which is very close to the value of the 97 gigapascal given for the brass in the table 6.1. Then after that, you need to find the yield strength, which is you need to use the concept of the offset. So in this case, they already done for you where they show you the offset. So the 0.02 strain offset line is constructed as shown in the intersect between the stress strain curve at approximately 250 megapascal, which is the yield strength of the brass. Okay, so you can see here, you bring the straight line, you draw the straight line until the straight line is actually intersect at the stress strain curve, and then bring to the left and then read the value. So it's actually approximately 250 megapascal. And you see the maximum load that can be sustained by the specimen, meaning they are asking you about the tensile strength. Okay, in this case, we use the formula that we know, sigma equal to the F over the A, right? And then you substitute the value, which is you know the value of the diameter. Okay, then you will get the value from Newton, 57.900 Newton. Okay, and proceed to the last question. They ask you to compute the change in the length. which is you know that the LO here over here the changes here. The E is equal to the changes of the length divided the original, yeah. The Li minus the L naught divided by the L naught. Here substitute the value, then you will obtain the 15 millimeter. Okay, right? Yeah? So now we move to the next of the properties. Yeah, that is actually is about the stress strain, and then we are looking for the ductility. So in order to examine the mechanical properties, especially for the ductility, yeah, we want to know the mechanical properties of the ductile or the brittle material. We can actually use the value ductility to identify it. Okay, so what we understand about the ductile material. So the ductile material is in which it is undergoes the extensive deformations under the action of the loads before it can be impelled. Yeah. So for example, in this case lah, yeah, it's extensive. What they call a deformation, yeah, under the load being given. Yeah. However, how about for the brittle? The brittle is material. Which undergoes a little deformation, for example this one, okay, under the action of the load before it fails. Yeah, so compared to the ductile, it's a massive, yeah, it's a massive changes compared to the brittle. Okay, so in this case, we can say, I mean, from the canister, it say that in order to define, to category the ductile, to the category what they call the brittle materials, it is not more than the 5% of the fracture strain. So in here, the definition of the ductile is a measure of the material's ability to undergo appreciable plastic deformation before it being fractured. So it can be defined by two methods. First, according to the percent of the elongation, which is denoted by the EL percentage. Yeah? So it is actually related to the strain. Yeah, related to the strain. Yeah, the final of the length sample after the test and before the test the L naught. Then you will obtain your percent elongation. So from there you can actually identify whether the material is in ductile or it is in the what they call a brittle. Alright. So the second part is using the percent reduction in area. Yeah, whereby that they say that is area. So in this case, you are finding the area after the break and also before the break. Yeah, and then get the percentage. So this is example. Yeah, example that you can use to recheck your concept understanding of the brittle. Yeah, and also the ductile. So in this case, the ductility, yeah, the ductility of the material here, a cylindrical specimen of steel having an original diameter of 12.8 millimeter in the tensile test to fracture and found to have an engineering fracture strength. It is a cross-sectional diameter at fracture is 10.7 mm. Determine the ductility in terms of the percent reduction. Okay, so here we know that the ductility can be computed using the equation given before this, where it's actually your reduction area, the area before failure, and minus the area before failure, the area after the failure divided by the original. Okay, then you will obtain 30%. Yeah, so in this case we cannot define it yet because we need to know we need to do the comparison. By law of the from the Callister books, for example, they say that the fracture strain here for brittle material, it is approximately not exceeding 5%. Then we call it as a what you call as a brittle, which means that by the time that it reaching, the reaching already before the fracture, it is actually less than 5%. So that way we can go conclude it as a brittle. Okay. Alright, so the toughness, the last of the property that under the tensile test that you can get, engineer, how would you define the toughness at the beginning? You need to ask yourself, how would you define the toughness? Okay, so toughness is a fundamental material property that measure the ability of material to absorb the energy and withstand the shock up of the forces. Okay, so in this case, the toughness also related to the area under the stress and strain. And the unit for the toughness is actually in the energy, J, the joule over the meter cube, can be measured by the impact test. Okay, in this case, so this is the toughness, under the curve. Yeah, so here the material with the high strength and also the high ductility will have the more toughness, compared to the if the material with the low strength and also the low ductility. Okay, so and we move to the true stress and strain. Yeah, the true. So the typical stress and strain curve. Yeah, the typical stress and strain what they call the curve for the ductile material is obtained by performing the tensile test again, like this you can obtain, but this is only approximation. It doesn't represent the actual stress or strain in the test pieces, during the tensile test. So in this slide we will talk about more on the what is actually the true stress and also the true strain. Okay, by default here, if you can see the engineering stress, here is the instantaneous load applied to a specimen divided by its cross-sectional area before any deformation. Okay, and then it is to determine the true stress and the strain value, which can be noted by the stress equal to F over the A naught, and also the strain is equal to the changes of the length divided by the original length. Okay, so the true stress here denoted by T here is the load divided by the instantaneous cross-sectional area AI, which is it is a continuous deformations, occurring, i.e. the neck, the past tensile point. So also the load is actually divided by the actual area in the neck down region, continuous to raise to the point of fracture, in contrast with the engineering stress. Okay. So here we can actually define it, whereby that if we actually, would measure, the true stress and also the curve strain, it would be like this. You can see it is actually starting the red color. The red color is actually represent your true stress and strain. So you can differentiate, between it from true curve and also the engineering by note it that engineering curve, this the blue color, the engineering curve drop after the necking, after the necking. So this is where, but for the true curve, it's always progressing, is always increasing. So you need to remember that the necking is a rapid reduction at the cross-section area test piece, which the value for the engineering curve reaching its maximum value, which is ultimate tensile strength. Okay, so we can say that this is not all for the cases. As a matter of fact, it is a in stress at certain of the cases. So the cross-sectional area is decreasing rapidly with the neck region where deformation is occurring. So the stress are computed by the equations. The common equations is on basis of the original cross-sectional area before any deformation and does not take into the account the reduction in the area of the neck. Okay, so remember, the necking is rapid reduction at the cross-section area. Let us be where that we know that it been dropping. It been dropping. Okay, okay. But why actually engineer use the value from the engineering rather than using the what they call the true value? because we know that at the same point that the value should be dropping after the necking. Yeah, so we have to actually, what we can conclude over here, we have to, be difficult actually to measure the instantaneous cross-sectional area during the tensile test. And most of the time we don't have the true stress strain curve. It's very difficult to find it. And secondly, we most of the time only analyze the designing things in which is only in the elastic region. Yeah, as you can see how actually the engineering and also the true value is actually almost similar at the region elastic. Yeah, it's almost similar at the region. However, for some cases, we when we have a large plastic, yeah, deformation over here, yeah, the deformation between these two curves, yeah, is significant due to the sudden changes or because of the cross-sectional area when necking occur. Then we need to use the true curve. So this is basically the formula that we will use in order to calculate the value of the true stress and also the true strain. Okay, so the original is over here, but then when we change it, this one to the F times L over the L over the minus L naught, you will obtain this one, yeah, the formula. Okay. Right, to summary, yeah, in our part 1 and part 2, okay, the stress and strain, yeah, these are the size independent measure of the load and displacement respectively. And elastic behavior, the reversible behavior often shows a linear relation between the stress and strain. To minimize the deformation, select material with a large elastic modulus. So the plastic behavior is actually this permanent deformation behavior occur when the tensile or the compressive unit axial stress reach. So this is actually the summary. What is actually what's the behavior? Yeah, deformation is occurred at the one each of the point over here during the elastic or during the yield, during the strain hardening. So you can see that here the summary of the strain stress diagram. Okay. All right. So I think that's all. Thank you very much for your time. Hopefully that we can get some information from this slide, and you might try to recap back what you learned in this chapter by doing the tutorial. I think that's all, and thank you very much.